Hi, and welcome to my final project for Chemistry 324 at Humboldt State University. In this video, I'll be demonstrating the three-dimensionality of molecules using VSEPR theory and these Plato models. VSEPR theory is used to predict the geometry or the shape of an individual molecule based on the number of electron pairs on the central atom. This would be the central atom, and these would be the atoms to its left and right. This molecule here, well, might as well begin. This molecule here is linear. A good example of this molecule would be beryllium chloride. This would be the beryllium, two chlorides. The shape of the molecule is linear, as you can see. The angle at that the molecule has is 180 degrees. That's the angle for a line. Another example of this molecule, or the shape, sorry, would be carbon dioxide. Carbon dioxide has this shape too, linear, except double bonds instead of single bonds. The oxygens would replace the chlorines in this case. And molecules that have this shape have an sp hybridization, two things attached to the central atom. Moving on, we have a trigonal planar shape. Notice there are three atoms attached to the central atom. The central atom I'm holding with my gloved hand. Notice the gloves. This is the time of a pandemic. You're not trying to catch the Rona. This molecule here, well, we could use this example as borane. We could use borane as a good example for this molecule. Borane, BH3, has an sp2 hybridization, just like this molecule here, just like the shape that you see in front of you. And the angle between the atoms on the sides is 120 degrees. If you see this as a circle on a piece of paper, and you divide it by 3, you can see that 360 divided by 3 would result in this 120 degree angle. Right here. Also here. On all three sides of it. Phosgene is another example of a compound with this molecular shape. Phosgene is a gas irritant. It has this shape as well. Our next molecular geometry is a tetrahedral, shown by the structure right here in front of you. Notice that this molecular geometry has 4 atoms attached to the central atom. Now, tetra means 4, that's why there's 4 things attached to the central atom. This molecule could be something like methane, CH4, something like silicon tetrafluoride, SiF4. The bond here between the angle between these two bonds here is 109.5. Notice it's not 90 degrees, even though on paper you see a circle with 4 sticks sticking out of it. That's because in 3 dimensions it looks like this. And that angle right there, on paper, it would be close to 90 degrees, but it's 109.5. This compound here has an sp3 hybridization. Up next, we have trigonal pyramidal, depending on where you're from. This shape here has 4 things attached to it, just like the previous molecular geometry that you saw, except notice that this compound has a pair of electrons up here, 2 electrons, making 1 pair. That pair is what causes the shift in shape of this compound because of the repulsion that those electrons emit. Pairs of electrons in a valence shell repel one another because of their negatively charged cloud. They form a cloud up here of electronegativity. I like to think of it as a spherical halo of negativity on these electrons, which pushes the electrons on the valence shells of these atoms here into the shape that you see, giving it a bond angle of 107 degrees. Notice it's less than 109 because it's not exactly spread out evenly through the sphere. The electrons that you see, the pins on the central atom, they push the other atoms to the sides, giving them that 107 degree angle. A good example of this compound could be ammonia, NH3. There's a lone pair on the nitrogen, which would be this central atom here. Another example of this molecular geometry would be phosphine. Phosphine PH3, I believe, has this same molecular shape. Last but not least, we have the bent molecular shape. This is sp3 hybridized. A good example of this shape would be water, H2O, the oxygen, the hydrogens. The pins that you see up here would be the 2 electron pairs, 4 total electrons on the central oxygen atom there. It is sp3 hybridized. I believe I said that already. Just like the previous 2 shapes are also sp3 hybridized. Water has a 104.5 degree angle. Notice it's smaller than 109.5 and smaller than 107. So the other sp3 molecular geometries have larger angles than this one. That's because of the double pair of electrons here. It creates greater repulsion this way, downward, closing the angle between these 2 hydrogens, making it even smaller. It's not exactly a 90 degree angle. Notice it's 104.5. It's a little bit bigger than 90 degrees. And that's created by that repulsion of those electrons up there. Anyway, thank you for watching.